Okay, so let's assume now that we've made this simplification where we say, I can actually model this fin, or this extended surface, as having only a temperature that changes in the x direction, and the y direction change is negligible. So if we make that assumption, now we can go through this analysis, derive a temperature expression, and solve it. So again, we'll see how far we get today, but let's have an attempt at it. So what I'm going to do is, let's see. Yep. So let's draw a control volume. I'm going to use the diagram I have here. Normally we do this in 2D, but let's try to do it in 3D. So I'm going to draw a control volume. That control volume is going to be what we'll do the energy balance on. So control volume here, I'm going to pick something in the middle. All right, so it has that differential width, dx. Let's say this is dx in this direction. And I need to keep track of what's coming in, what's leaving, and any generation, energy stored, that kind of thing. So like always, we have conduction, right? So we're modeling only in x, right? We're only modeling heat, a temperature gradient in x. So we have q dot at x going into this. Leaving, we have q dot at x plus dx. All right, let's say we don't have generation. We're not dealing with that in this scenario. Let's say it's steady state, so du dt is 0. So that's fine. We have something else going on. Right? You have convection going on from the surface. So from this control volume, we have, where do I put this? Q dot convection. That Q dot convection is at x, right? And because the temperature is changing as a function of x, Q dot convection is changing as a function of x as well. So no longer do we have like a constant that you can throw in there. There's a function for temperature for that, and we have to include it. Okay, so let's go through and write that out. So it looks like this: Q dot x minus Q dot x plus dx minus Q dot convection, which is a function of x, is equal to 0. That's our control volume energy balance. So now let's introduce rate equations here. First of all, let's say Q dot convection, which is a function of x, is equal to h bar times, let's call this dAs, times t at x minus t infinity to the surroundings temperature. So a couple things here. H bar, let's just assume that's a constant. T of x we don't know, right? We're trying to solve for temperature, so we don't know that. We just know that the heat transfer is related to that particular temperature at whatever that position is. dAs, that's some differential area. So that's actually h bar times, what's the differential area that's exposed to the surroundings? Yeah, go ahead. Yeah, dx times the whole perimeter, right? The perimeter of the fin. So let me just draw it this way, right? This perimeter times dx. That's the surface area that's exposed for that differential element. So let's write that out. So this would be, this would be perimeter dx times, again, t. I'll just leave this as t as a minus t infinity. So just remember that t is a function of x. It's something we're trying to solve for. So that's our rate equation for convection. The conduction stuff we've already done, right? We can go back and just do that the same way. So let's just expand this out. Q dot x minus Q dot x plus dq dot x dx dx minus now h bar perimeter dx t minus t infinity is equal to 0. So that's just enforcing the energy balance on the control volume. And then let's cancel some stuff out. So let's see, Q dot x goes away, right? Minus, plus minus there. And then everything that's left has this dq dot x is multiplied by dx. H bar perimeter is multiplied by dx, so dx can cancel out as well. Remember I said that's really important. If you can't cancel dx, you have a problem. So dx cancels out. And we're left with the differential equation for this, which is minus dq dot dx minus parameter times h bar times t minus t infinity is equal to 0. Okay? So this is our governing differential equation in terms of heat. We need it in terms of temperature. So introduce Fourier's law. Fourier's law gets substituted in for q dot. So that looks like this. So minus, minus d dx of Fourier's law minus k ac dt dx minus parameter times h bar times t minus t infinity equals 0. So we can, let's see, conductivity, let's assume is constant. Cross-sectional area, AC. By the way, what cross-sectional area am I talking about now? Right, it's not the one in the y direction, it's the one in the direction we're modeling, in the x direction. So that blue perimeter, that outlines the cross-sectional area that I'm talking about. Right, so keep your areas straight. So that's constant, that's not changing as a function of position for this fin. So some of that stuff can be divided out, and we can simplify this down to this ODE, which is d squared t dx squared minus perimeter h bar over k ac times, let's see, I'm going to run out of room, times t, I'll do this, okay, yeah, t is equal to, now on the right-hand side, we have another, sorry, I have to make some more room here, problems. Let's move that over here. Okay, sorry, this is not going exactly how I wanted it to. Let's move this over. But I want you to see the complete final answer. So d squared t, so then on the right-hand side we have minus perimeter h bar over k ac times t infinity. Okay. So first of all, why did I go to the trouble of moving stuff around? I'm not that anal. But what I wanted to show you was, this is the standard form of the ODE. The standard form means a specific thing. It means your highest order derivative in temperature is by itself. Right? So d squared t dx squared is by itself. It also means that all stuff having to do with the independent or the dependent variable t is on one side, anything else is on the other side. So if I say write something in standard form, I mean this, right? Nothing multiplying d squared t dx squared. All temperature stuff on the left-hand side, anything left over on the right-hand side. And the reason why you want to do this is because it hints at the solution that you have to make. Okay. Any questions on how we got this far, or confusion?
One thing, when you draw q dot convection in the x direction, is it actually going out from all sides of that thing? Okay.
Question was, when I drew it like in the x direction, is it going out everywhere? So yeah, like you can think of it as, I don't know how to draw it very well, but like it's leaving every possible direction. Right? The directionality is not actually important, it's just noting that it's leaving the control volume.
So are the areas for conduction and convection the same in this case?
Question was, area for conduction and convection the same? No. So the area for conduction is the area in the area that's sort of, when I say like available, I'm thinking, you know, you try to, let's say you're trying to like draw in liquid through a straw, right? The bigger the straw, the more liquid, the easier the liquid's going to come. So the area that's available is that cross-sectional area. Same thing for heat transfer, right? You're looking at sort of that constricting area that's available. So here we're looking in the x direction. The cross-sectional area is that perimeter of the fin, right? For convection, we're looking at what's available for it to leave that control volume, which is the differential width. Okay. Question?
So then the perimeter of the fin, the area of the top and bottom, and the two side surfaces added together.
Yes. Area of the perimeter of the fin is the top, bottom, and two sides. If you have a really long fin, sometimes you can make the simplification that the sides don't matter, right? It's just the top and bottom.